In the name of Almighty God, I am Mahsa Hassankashi, and today I want to talk about electrical impedance spectroscopy. Electrical impedance spectroscopy is a technique that characterizes the electrical properties of a material or system by applying an alternating current signal over a range of frequencies and measuring the resulting current. By analyzing how the system's impedance, a measure of total opposition to current flow, combining resistance and reactance, changes with frequency. It is possible to gain insight into the material's structure and function. This method is used in various fields including battery research, corrosion studies, material science, and medical diagnostics to understand properties like resistance, capacitance, and reaction rates. And how it works. The first step is applying a signal. An alternating current or AC voltage is applied to system or material across a wide range of frequencies, from very low millihertz to very high megahertz. The next step is measuring the response. The resulting current is measured. This current is shifted in both amplitude and phase relative to the applied voltage. The next one is calculating impedance. Impedance is calculated as the ratio of the AC voltage to the AC current. It is a complex number that includes both a real part, which means resistance, and an imaginary part, or reactance, which can be graphed to visualize the system's response across frequencies. The next one is interpreting the results. The impedance spectrum, often shown as Nyquist plot, provides information about the different electrical components and processes within the system, such as the resistance of the bulk material, the resistance at interfaces, and the capacitance of different layers. And what are the key applications? The first one is battery and fuel cell research. Electrical impedance spectroscopy is used to measure the internal resistance and study dynamics of batteries and fuel cells, which is crucial for assessing their performance and health over time. The next application is corrosion testing. It is used to evaluate the anti-corrosion performance of protective coating by measuring their impedance, which changes as corrosion progresses. The next one is material characterization. Electrical impedance spectroscopy helps determine the electrical and dielectric properties of materials, including transitions like glass transition or TG and ferroelectric transition or TC. The next application is biomedical diagnostics. The technique can be used in biosensors to detect specific biomolecules such as DNA or cancer biomarkers, or to monitor cell interactions at an electrode surface. The next application is quality assurance. It plays a role in quality control for chemical and pharmacological processes and the manufacturing of electronic components. The next one is electrochemical, relates to the study of chemical reactions involving electron transfer, specifically the relationship between electricity and chemical change. It describes processes where chemical reactions generate electricity, like in a battery, or where electricity derives a chemical reaction, like in electrolysis. These processes are key to technologies such as batteries, fuel cells, and some methods of water purification. Key aspects of electrochemistry. The first one is electron transfer. Electrochemistry is the science of electron transfer across a solution electrode interface involving oxidation or loss of electrons and reduction gain of electrons, known as redox reaction. The next one is electricity generation. Spontaneous chemical reactions can produce an electric current when channeled through a device called an electrochemical cell, which is the principle behind the batteries. The next one is electricity usage. Electricity can be used to drive a non-spontaneous chemical reaction, making it clean reagent in processes like wastewater treatment. The next application is electrochemical cell. This is a device that either generates or uses electricity. A common example is a battery, which consists of anode and a cathode in an electronic or electrolyte solution. The next one is electrochemical series. This is a list of elements arranged by their standard reduction potential, which indicates the tendency of metals or lose or gain electrons and determines their strength as reducing or oxidizing agents. Spectroscopy is the study of the interaction between electromagnetic radiation or light, like light and matter, used to determine an object's composition, temperature, density, and motion. It works by analyzing the spectrum, the range of wavelength, colors, or frequencies that matter absorbs, emits, or scatters. This technique is used in fields from astronomy to medicine, with applications like determining the chemical makeup of distant stars or visualizing soft tissue inside the body using magnetic resonance imaging or MRI. And how it works. The first step is interaction with matter. Spectroscopy is based on the principle that matter interacts with electromagnetic radiation in specific and predictable ways. Atoms and molecules absorb or emit photons of specific energies, which correspond to specific wavelengths or frequencies. The next is splitting light. An instrument called a spectroscope separated light into its constituent wavelength, much like a prism separates a white light into a rainbow. The next is analyzing spectra. The resulting spectra can be a continuous spectrum like a rainbow, an absorption spectrum where specific wavelengths are missing because they were absorbed by the material, or an emission spectrum where only specific wavelengths are present because the material is glowing. The next is identifying elements. Each element has a unique set of energy levels, resulting in a unique absorption and emission spectrum. By analyzing these unique patterns, scientists can identify the elements present in a substance from a start to a chemical sample. And what are the applications? The first application is astronomy. Scientists analyze the light from celestial objects to determine their composition, temperature, distance, and speed. The next application is in chemistry. Spectroscopy is used to identify and analyze the structure of molecules in organic compounds and other materials. The next application is medicine. Techniques like MRI use spectroscopy to create detailed images of soft tissues inside the body. The next is forensics. It is used to perform qualitative and quantitative analysis of samples in forensic laboratories. This simulation provides the theoretical background, the principles and applications of electrochemical impedance spectroscopy in various research and technological sectors. The simulation is starting with basic knowledge on sinusoidal signals, complex numbers, phasor notation, and transfer functions, continuing with the definition of impedance in electrical circuits, the principles of the electrical impedance spectroscopy, the validation of the experimental data, their simulation to equivalent electrical circuits, and ending with practical considerations and selected examples on the utility of electrical impedance spectroscopy to corrosion, energy-related applications, and biosensing. A user interactive Excel file showing the nyquist and both plots of some model circuits is provided in the supporting information. This simulation aspires to provide the essential background to the graduate students working on electrical impedance spectroscopy, as well as to endow the knowledge of senior researchers on various fields where EIS is involved. We also believe that the content of this tutorial will be a useful educational tool for EIS instructors. And what are the applications? Electrochemical impedance spectroscopy or EIS is a versatile technique used to analyze chemical systems non-destructively in fields like energy storage, corrosion, and biosensing. Its applications include characterizing batteries and fuel cells, evaluating the durability of coating, studying biological interactions of diagnostics, and analyzing the performance of solar cells and semiconductors. And what about energy storage and conversion? The first one is batteries. Electrical impedance spectroscopy helps diagnose and monitor the state of health of batteries, including lithium-ion batteries, by separating contributions from components like the electrolyte and electrodes. It is crucial for studying battery degradation and aging. The next is fuel cells. It plays a vital role in the development, manufacturing, and analysis of fuel cells. The next one is solar cells. Electrical impedance spectroscopy is used to analyze the performance and properties of solar cells. And what about corrosion and material science? The corrosion. Electrical impedance spectroscopy evaluates the durability and corrosion rate of coating and is used on-site to assess their integrity. It can detect delamination and water uptake even before visible damage happens. And the next one is material characterization. It is used to study the processing structure property relationships of materials like semiconductors and composites, including interfacial effects between particles in a composite. And the next is sensing and diagnostics. The first is biosensing. Electrical impedance spectroscopy is used to understand interactions at electrode surfaces for biosensing applications such as detecting enzymes, antibodies, ions, and viruses. The next is biomedical diagnosis. It can be used for important biomedical diagnostics applications by analyzing events at a biomodified electrode surface. The next one is emul- emulsion analysis. Electrical impedance spectroscopy can determine the type of emulsion, for example, oil in water, and can also assess other phenomena. Electrochemical impedance spectroscopy at one glance. Electrochemical impedance spectroscopy offers kinetic and mechanistic data of various electrochemical systems and is widely used in corrosion studies, semiconductor science, energy conversion and storage technologies, chemical sensing and biosensing, non-invasive diagnostics, and etc. Electrochemical impedance spectroscopy is based on the perturbation of an electrochemical system in equilibrium or in steady state via the application of sinusoidal signal, AC voltage or AC current, over a wide range of frequencies and the monitoring of the sinusoidal response current or voltage respectively of the system toward the applied perturbation. Considering that the electrochemical system under study is a linear time invariant system, that is, the output signal is linearly related to the input signal and the behavior of the system is not changed over time. Electrochemical impedance spectroscopy is a transfer function technique that models the output signal AC current or AC voltage to the input signal AC voltage or AC current over a wide range of frequencies. The importance of electrochemical impedance spectroscopy over other electrochemical techniques lies on its ability to discriminate and thus to provide a wealth of information for various electrical, electrochemical, and physical processes take place in a real electrochemical system. This task is very challenging as all these different processes exhibit different from very fast to very low time behaviors. The resistance of a liquid electrolyte, the different bulk and grain boundary conductivities when a solid polycrystalline electrolyte is employed, the changing and charging, the discharging of the electric double layer at the electrolyte interface. The dependence of the capacitive behavior of the electric double layer on the morphology of the electrode surface and composition of the electrolyte, the kinetic of an electrode charge, the transfer reaction, homogeneous reactions, and adsorption and desorption phenomena coupled with the electrode charge transfer reaction, mass transfer phenomena, diffusion of species to the electrode surface, and etc. Exhibit different time constants. For example, tau, a measure of the time behavior of a process. This time constant of a process is given as where R is the resistance of a resistors in ohms and C is the capacitance of a capacitors in farad. And note that time constant is in time unit in second. And the formulation is 1 ohm multiplied by 1 farad is equal to 1 volt divided by 1 ampere multiplied by 1 coulomb divided by 1 volt is equal to 1 coulomb divided by ampere is equal to 1 second. Notably, electrochemical impedance spectroscopy measurements at an electrochemical system can be simulated to an equivalent electrical circuit which consists of common passive components such as resistors, capacitors, and inductors, and others. More complicated referred to as distributed elements connected each other in different ways. In other words, each of these processes can consequently be deemed analog to an equivalent electrical circuit that is characterized by a different time constant. For this purpose, most electrochemical analyzers are provided with suitable software enabling the simulation of the impedance data to a model circuit. A specialized equivalent circuit modeling software such as ZView and ZPLOG uh, is also available. A prerequisite for the simulation of the electrochemical impedance spectroscopy data to an equivalent electric circuit is that the validity of the data has prior been evaluated. This can be done by running the so-called Kramer's Kronon test, which is available in most software provided with electrochemical analyzer. Considering that the first one is there is not a unique model circuit for a given impedance spectrum, and the next one is the quality of the modeling increases with the number of the components included in the circuit, the better. It is important that each component is correlated to an individual process by scientific logic. When working in the time domain, as with one of the commonly used voltammetric techniques or cyclic voltammetry, a Cron technique, or etc. Some of these processes is very difficult, if not impossible, to be analyzed. On the other hand, when working in the frequency domain or a wide range of frequencies, electrochemical impedance spectroscopy simplifies a complex electrochemical system by deconvoluting it in individual processes with a different time constant, which then can be easily analyzed. Very slow processes can be probed in very low frequencies, while very fast processes can be probed in very high frequencies. Practically, the frequency range is dictated by limitations associated with the available instrumentation. The wiring of the electrochemical system with the instrument high frequency limit and the stability of the electrochemical system itself over time, which means a low frequency limit. The frequency range in most of the commercial available electrochemical analyzers spans from 10 microhertz to 1 megahertz. For more specialized applications such as the study of ionic motion in polycrystalline solid ionic conductors, a very fast process with a very small time constant at the microseconds range. The first one, some vendors offer instruments enabling excitation frequencies at some megahertz. On the other hand, in practical applications, the lowest frequency limit is limited to 1 megahertz, often at 10 to 100 megahertz, as the time required for a measurement to be conducted at these frequencies is very long. For example, at 10 microhertz, a single measurement takes 1 divided by 10 to 5 hertz is equal to 105 seconds is equal to 27.8 hour. Typically, an electrochemical impedance spectroscopy spectrum containing measurements at 60 frequencies over the range from the 100 kilohertz to zero point 0.1 hertz. Based on a logarithmic distribution, 10 frequencies per decade takes about 2 to 3 minutes. A comprehensive paradigm on how to estimate the frequency range that is required for the electrochemical impedance spectroscopy study of a typical electrochemical process, including a Faraday reaction with a rotating disk electrode, is given here. The response of this system to a certain perturbation, for example the resulting AC current to a small amplitude AC voltage perturbation typically superimposed over a DC voltage related with the formal potential EO of the redox couple, is governed by three processes: the charging, discharging of the electrical double layer at the electrode and electrolyte interface, the kinetics of the Faraday reaction, and the diffusion of the redox species from the bulk solution to the electrode surface. Each process exhibits a different time constant according to the given set of data. The time constants and the characteristic frequencies shown here. For the charging and discharging of the electric double layer, the Faraday reaction and diffusion are 0.04 milliseconds, which means 4.1 kilohertz, and 0.51 milliseconds, which means 310 hertz, and 0.41 second, which means zero point 0.4 hertz, respectively. Thus, for this specific example, the frequency range necessary to cover sufficiently the higher and the lower calculated frequencies can be from 10 kHz to 10 MHz. It is noted, however, that in practice the frequency range is not calculated but is selected in an experimental logic. Below, we will see and explain in detail that is in the most typical graph for the representation of impedance data. The so-called Marquis plot, a time constant, can ideally be visualized as a semicircle. Most of the electrochemical impedance spectroscopy textbooks front page illustrates narcotic plots involving successive semicircles. At the peak frequencies of these semicircles, the highest point of the arc holds the equation of 2 multiplied by p multiplied by f p and rho is equal to 1. Impedance spectroscopy comes from the world of physics and electronics and has been applied to electrochemical systems only since the second half of the 19th century. It is a generic method that is used in any application field of electrochemistry but also in materials, as an conductive materials has a specific dynamic electrical behavior that can be characterized by electrochemical impedance spectroscopy. In electrochemistry, the ultimate point of electrochemical impedance spectroscopy is to characterize an electrochemical process, but it can also be used as an optimization tool for electrochemical devices and applications as wide-ranging as material protection. Electrocatalysis is fuel cells and photocatalysis, electrochemical biosensors, photovoltaics and solar cells, solid-state and desensitized, redox flow batteries, and type of secondary batteries. At a glance, electrochemical impedance spectroscopy is a powerful technique. Electrochemical impedance spectroscopy is used to study a wide variety of systems in many fields of electrochemistry, such as electrode kinetics, double layer studies, batteries, corrosion, solid state electrochemistry, bioelectrochemistry, photovoltaic systems. The following two tutorials will give more specific information about using electrochemical impedance spectroscopy with battery and corrosion applications. Electrochemical impedance spectroscopy is a sensitive technique. It can measure tiny signals, so as with all sensitive techniques, certain precautions should be considered with electrochemical impedance spectroscopy. These are explained in the following simulation and experimental conditions. The purpose of this application and simulation with capsule software is to understand electrochemical impedance spectroscopy, Nyquist, and both plots. The application lets you vary the bulk concentration, diffusion coefficient, exchange current density, double layer capacitance, and the maximum and minimum frequency. Electrochemical impedance spectroscopy is a common technique in electro analysis used to study the harmonic response of an electrochemical system. A small sinusoidal variations is applied to the potential at the working electrode, and the resulting current is analyzed in the frequency domain. The real and imaginary components of the impedance give information about the kinetic and mass transport properties of the cell, as well as the surface properties through the double layer capacitance. And here you can see the components, the geometry, and the electroanalysis or TCD that I have used here for one-dimensional line. And the next one is that you can see the impedance with respect to the ground or Nyquist, and impedance with respect to the ground real part, and imaginary part or reactance. The next is concentration with all species. I can see that spatial coordinate and also concentration according to mole divided by cubic meter. The next one is concentration rate and concentration OX. Thank you so much for watching my video until the end, and also you can download this simulation from github.com/Mahsa script.